Okay, so in the last video, we talked about splitting, and we said these mainstream signals can be split into multiple tinier signals if we take a closer look at them, and those can be singlets and doublets and triplets and quartets and multiplets and so forth. And we kind of equated the number of signals minus one, which is equal to the number of protons. Or in the other way, if I take a look at a structure, I look at adjacent hydrogens on all sides, and then I take those hydrogens, I add them up, and I plus one on that total, and that could give me an idea of the actual splitting that's happening in an NMR. So now what I want to take a look at are these maybe exceptions that we would see to the rule, because you all know in every single class there's exceptions. You go to the math class and there's exceptions on this and that, and you go to chemistry, general chemistry, and there's exceptions on this and that, and then you go to another class and there's exceptions on this and that. It's like, what are we even doing? But there's so many exceptions out there sometimes that it doesn't make any sense. So there are exceptions with NMR. We're not going to go into all of them. We're just going to go into a few. And the first one that you need to know is there are times where we get no split at all, no split here, nothing to see. So there's going to be times where no splitting will happen, and what we will see in an NMR is a signal, and that signal will go whoop and whoop all the way back down, and it will not split into multiple tiny little signals. It'll just be one. So we have to talk about, well, when would this be the case? All right, so let's take a look at a molecule like CH3Br. Okay, so if I take a look at CH3Br, I'm going to ding dong that CH3 group, and that means we've got a signal. So that signal is going to show up in NMR. We know it's going to be present. We know that just because it's a CH3 group on a bromine group, we have a predictability of where this thing is going to happen, and it doesn't really matter where. That's not what this is about. It's about splitting. So wherever that major signal is going to be, will that signal split into multiple pieces that we need to take a closer look at? So the idea of splitting is all about neighbor protons. All right, well, this is pretty easy. It's kind of predictable, right? So if I take a look at this particular carbon, well, there's no neighbor to the left, and there's no neighbor that carries protons on the right. So because I don't have any adjacent protons, look at this. There are no adjacent. That is the key word here. There's no adjacent protons at all. And because of that, we get a 0, because there's no adjacent proton, plus 1. And that means it is one signal in total. That's all that you will see, and that is it. And that's exactly what we would see on an NMR. There are no splits that happen in this particular case. So I wouldn't necessarily call this an exception, right? It's just something that's not very ordinary, or it's something that's not very common, unless we're working with very simple compounds that are not fancy as far as the structures go or what's actually there, or maybe some type of appendage that's hanging off of a main carbon chain. Those sometimes do not split just because they do not have a neighbor that will do it for them. All right, so there's one example. Again, not an exception. I think that if I just gave this to you, I hope that you would look at this and say, well, there's no adjacent carbons, and because there's no adjacent carbons, it's a 0, and that formula is 0 plus 1. So that means one signal, and that's all that we get, and sure enough it is. So no splitting at all. Another thing that will also, and this is what I would call a trick, or an exception in a way, is what if we have a molecule that looks like Cl and then CH2 and CH2 and Cl? What if we have something that looks like this? This is also no splitting, and this is why. So if we take a look at the structure and we do what we've always done, I'm going to ding dong the molecule. So we're going to ding dong right there, and that is a signal. And then if I move on to the next carbon, I don't ding dong that one, and the reason is because they are equivalent. So these two things are equivalent, and I want you to get into the habit of doing the A's and the B's and the C's and the D's. I think that it will help you in the splitting when you get to that point. So this is a signal, and this is the same signal. So we're going to give both of these an A, okay? So if I take a look at the CH2 group, then I would look at this and I would say, all right, we're going to get a signal from that CH2 group. So wherever that signal is, that's where we start. And I will see a big major line that's going to show up. And now I need to kind of fine tooth this a little bit. And then when I go in and take a look and closer look at the baseline, is this thing going to split on me or not? So most of you at first glance would look at this neighbor carbon and you would say, oh, look, there's two adjacent hydrogens that are there. And those two adjacent hydrogens, well, that basically means two hydrogens, and those two hydrogens will plus 1, and that will give me a 3, and this looks like it would be a triplet, so I would see maybe a little spot here and maybe a little spot there. I would see 3 in total. Wrong. That's not how this works. And the reason is because equivalent signals do not split each other's signals. You have to keep in mind that these signals are the same, right? So because the signal is the same, they do not split each other's signals because of that. And this is one of those, what I would call a true exception to this rule about splitting. So because this is A and because next door is A, that's why I like for you to label these signals so that way it doesn't catch you off guard. Because those are equivalent, we do not count adjacent hydrogens in this case. So we pretend like those hydrogens are not even there, right? Now, if there was another proton on this side, or if there was another proton on this side, then we possibly will see some splitting that begins to happen here. But because there weren't, again, very simplistic molecule here. We're starting baby steps. Chlorine to the left, equivalent proton to the right. Then that is an identical match, and I don't have to worry about anything to the left or to the right-hand side of that thing. So no splitting will happen here either. I pretend like what I have here are no adjacent hydrogens. Even though there are, I pretend like there's no adjacent hydrogens at all. So I will see one major signal that comes from this thing, and that's it. Okay, so now we're going to take these concepts and we are going to build on top of them. We know the basics about how splitting works. And now we know two exceptions. I need to look for, of course, no adjacent carbons at all. We know how to handle that now, or hydrogens, protons. And then now I know how to handle if the signal is identical to the next one over. So we need to build upon this concept, and we need to get a little more complicated as far as example problems are concerned. All right, so now let me wipe this screen, and we're going to do another example that's going to include a functional group. All right, so a functional group is this carbon double bond OO. What is that functional group called? Well, if you've watched the previous videos, you should know this. And then you're going to say, oh, Mr. Tracy, I know this. This is going to be called an ester. The carbon double bond O is a carbonyl, and that carbonyl with an oxygen off the side of it is an ester. And what I know about esters is that they smell really, really good or really, really bad, but most of them smell really good and fruity. And then I also know how to name these esters, and those esters are going to be called O8s because that's how esters end, in O8s. Okay, good job. Good for you. I hope that's where your mind went. I hope that you didn't sound that way, but I hope that's where your mind went. So off of this ester functional group, let's do a CH3 group that's here. And then on this side, let's do a CH2 and a CH3. So I'm going to walk you through the type of problem that you might see within the NMR world. So the very first question that would probably come to you would be, here's a structure. Please identify the number of chemical shifts that you will have. All right, so if I take a look at the structure, we've done plenty of these examples at this point. If not, just go back and rewatch some of those videos, right? So I would look at this and I would say, okay, well, here's kind of the electronegative area. And I would say, ding dong. dong, there's one there, and then this one's different. Ding dong, so there's one there, and then the CH3 group is different than that CH3 group because that one's connected to an O and this one's not. So ding dong, I would see 3. So I would see 3 major signals that show up on NMR, and I'm just going to randomly put them on an NMR. It's all make-believe, folks, right? So here we are, we're just randomly going to place them. The next thing is that they might say, now rank them. Okay, rank the one with the lowest frequency with A and then rank them up accordingly. A, B, C, D, and so forth. So I would look at the electronegative area, and that's where a lot of my protons are going to be, and that electronegative area looks right in here. Okay, so that's the electron sucker I need to stay away from, and this CH3 group over here to the left-hand side, it's the furthest away. So that's going to be A, and that probably means that this will be my A signal here, closer to the 0 mark on the delta scale. All right, so the next one in line, well, what would I have? Well, I've got this CH2 group that's near that carbon, and I've got this CH3 group that's near that oxygen. And we've kind of seen this example problem before, right? So this CH2 group that's near the carbon, well, that does have an electron puller on it, but this one's directly connected to an electron puller. So this is probably going to be the next one in line for me. So that means that this one's probably going to be B. And then the next one and the final one is the one directly connected to the oxygen. And that is an electron puller. It pulls the electrons away from that carbon on the end. The electron cloud is a little bit less dense, and those hydrogens are more exposed, and they relate to the magnetic field a little bit stronger, and it takes a little bit more energy to get them to flip and all the way back down. So this is going to be C. So now I've predicted the number, and now I've predicted the order. Now we can add on a part C to these questions. And the part C will be, how do they split? We've labeled the equivalents, if there were any. We've determined the number of signals, and now we have went through this idea of how do they split. Okay. So if I take a look at A, what is next door? It's a different signal. They're not equivalent. There's 2 protons here, so 2 plus 1 is 3. So I would actually see 3 separate, very close together signals that show up at that location. And that triplet would let me know that a neighboring or neighboring carbons are carrying some protons, and the total number of those protons would be 2, because 3 minus 1 is 2. All right, up next is B. So I need to look for adjacent protons, and here to the left, well, we've got adjacent protons. There's 3 of those. And then to the right-hand side, because that's adjacent to it as well, that carbon doesn't have any protons. So that's an easy one to take care of. So it looks like I only have 3 to the left to worry with. So therefore, 3 plus 1 is 4. And this will split into a quartet. So on the NMR, I would probably see 4 signals, 4 lines that are really, really close together that come off at one time. And that is in reference to the number of adjacent carbons. So I would look at those 4 lines, and I would say, well, at that major signal, I've got 4 minus 1, 3 protons. And those 3 protons could be on either side, or it could just be on one side, or it could be on both sides. It could be up, it could be down. It could be around it in some form or fashion, but they are adjacent at least to that signal where that one shows up. Okay, that's the information that it will give me. And then finally, on the other side, we see the CH3 to the right. So if I look over at the CH3 group and I go right-handed, there's nothing there, right? So I don't have to worry about protons there. And then over on the left-hand side, there's no protons that are there on that adjacent position either. So I do not see any proton at all. 0. Zippity-doo-dah. Mary Poppins. 0. So the 0 proton is 0 plus 1 is 1, and this would be a singlet that happens at position C. So that does actually not split at all. It is one signal only at C, and that's how we would describe that. So C is going to be a singlet, and then B is going to be a quartet, and then A is going to be a triplet. All right, so keep in mind it goes both ways, cup half full, cup half empty. So at any point in time, I could give you the structure and say, describe the NMR, or I could give you the NMR and say, describe the structure. So if you had to go backward, you would look at this NMR and say, Tracy, I've got this. Not a big deal. Not a problem. I know that there's 3 major signals. 1, 2, 3, because there's 3 major lines on the graph. And then when we zoom in, it looks like this has broken up into a triplet. So I know that the adjacent positions will have 2 protons in total, and then here's a quartet, so I know the adjacent position to that one, or positions, will have 3 protons in total, and then here is a singlet, and that singlet means that at that particular location, the neighbors do not have any protons at all that I need to take care of, because it is a singlet and it's one line and one line only. So that is how we would describe what we are talking about on an NMR. Now, there is a proper term that comes along with this, and this proper term is called multiplicity. Did you ever watch that movie? Is that what that movie was called? Multiplicity, with Michael Keaton. So multiplicity, we're referring to the terms of singlet and quartet and triplet and multiplet and those types of words. That's what we were after. So if you're running across problems, or if you're reading literature and it talks about the multiplicity of signal blah 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 is going to be a doublet, well, that's what that means. It's multiplicity. Calculate the multiplicity. All right, and then name the multiplicity. You will often see those every time in the literature and in example problems. All right, so now let's take a look at another example problem that's very similar to this, but slightly different. Because again, we're going to go slow and we're going to build up on these molecules until we go a little bit more and more complicated with them. All right, so this is the structure I'm now going to give you. So what type of structure is this one? Oh, it's an aldehyde. I know that because we just talked about carbonyls, and carbonyl family type 2 is aldehydes and ketones, and that's an aldehyde. It's a C double bond OH. I know how to name those. These names end in AL for aldehyde because aldehyde starts with AL. All right, we all went through those lectures. At least I hope you did, and at least I hope you paid attention. So if I take a look at this structure, we're going to get the same types of questions. Number 1, how many signals does the molecule show in NMR? Okay, so we look at this and go, oh, signals, all right, well, this carbon has a hydrogen, ding dong, and this one has hydrogens that's different, ding dong, and that one's got hydrogens that are different, ding dong, and this one has hydrogens that are different, ding dong. They all have signals that they're going to show up on the NMR. They're all different from each other. Why is this CH2 group different than this CH2 group? And the answer is, look what they're connected to. This CH2 group on the right-hand side is a carbonyl bond, right? A carbon with a double bond O. Well, this CH2 group is not connected to a carbonyl, is it? It's got a methyl group onto the left and another CH2 group on the right-hand side. So that's why these are not equivalent. They are the same as far as the way they're written, CH2 and CH2 at face value, but in NMR, they are not. They are not equivalent at all. So what I'm going to see in the NMR, I'm just going to draw a line, randomly put things on it. I'm going to see 1, 2, 3, 4 signals, right? All right, so 1, 2, 3, and 4 signals. We'll just do this kind of so we can start putting the pieces of the information together. So off of this thing, I'm going to then order them up because it's probably going to be the next question, or I'm going to see questions that way, right? So I'm going to order them up because I know there's going to be an A, B, C, and D. So if I look at this molecule, here is the electronegative area of the molecule. We've got one, it is the oxygen. So the furthest away from the oxygen is going to be the easiest ones to flip. So that means that this CH3 group, that's probably going to be the first one. That's going to be my A on the signal. It will be the earliest that flips. It will be the easiest that flips. So therefore, it will be the one closest to the 0 TMS. And this will be my A category right there. So now we'll take a look at what's next in line. Okay, so if my electronegative area is here, well, that proton is smack dab on top of that one. And then this one's a little bit further away, and this one's a little bit further away. So that probably means that this one is going to be B, and B is going to show up here. And then what's next in line? Well, okay, this proton on that carbon's connected to a carbon with a double bond O, but this one's directly connected on the carbon with the double bond O. So which one do you think is going to get bullied the most at the lunch table? It's going to be this poor hydrogen over here on the right-hand side. So that means that this is going to come next in line, so that will be C, and then this one will be D. That hydrogen has no friends. It's all alone at the lunch table. It is easy picking for that oxygen, and that oxygen's going to go in and wham, bam, take your lunch money and leave. And that's what that proton's going to all the way home. All right, so A, B, C, D, that's the order. Next is the splitting, because now we can go another step further. And we know that splitting is going to be adjacent hydrogens. And there's a few on here that's going to be pretty easy in order for us to figure this out. So I'm going to start taking a look at A. I think A will be the easiest because next door, hey neighbor, how are you this morning? And then that carbon's going to say, I've got 2. So you're going to look at this and say, oh, okay, well, there's only one neighbor. There's 2 protons that are there. So 2 plus 1 is going to be 3. So that means that A will be a triplet there. That's what that means. That's what splitting is all about. Okay, so then I'm going to do another easy one at least, and that is D. So that carbon that has the proton on it, that is the D signal. So we need to look for the neighbors to that particular carbon where that one is located. And there's only one neighbor on that side, right? So this one is that CH2 group that is here. So hey neighbor, how many kids do you have? And that carbon's going to say, I've got 2. Do you want them? Because I don't need them anymore. Take them, please. They've made me miserable. And that carbon's going to go, no, I don't want them. I just wanted to know how many that you had. So there's going to be 2 and 1 on the way. So 2 plus 1 is 3. And that means that that signal is going to be a triplet as well. So we've got 2 triplets that are going to be here. All right, the next one that I want to do is going to be C. And here's why. I think it might be the easiest to take a look at. It's also the lowest out of the 2 left to take a look at. So if I look at C, I'm going to go adjacent houses. So over here to the left, knock, knock, knock. Hey, carbon, how many kids do you have? And that carbon's going to say, I've got 2. I don't want any more. And then that carbon's going to go the other next door, and it's going to go and knock, knock, knock. And it's going to say, hey, carbon, how many kids do you have? And that carbon's going to say, I've got 1. Okay. So I'm looking at this, and for that particular signal, I've got one side, 2. Well, what did we say the rule was? 2 plus 1, 3. And then on the right-hand side, that carbon told me it had 1 kid. And I do the same thing there. I add 1. That gives me a 2. So what do we do with these? Do we add them up? No, you don't add them up. Because they actually affect each other. They kind of play off of each other. I've got two crazy kids on the left-hand side with one more on the way. And then I've got one crazy kid on the right-hand side with one more on the way in that house. And then before you know it, I'm going to have 3 and 2 out in the streets running and screaming and being crazy with each other. And they just multiply and amplify each other's antics even more so. So, 3's bad enough. 2's going to be bad enough, but by the time you put 5 out into the street, you might as well put me in the loony bin because I don't want to be anywhere near it. They're just going to multiply and amplify each other's bad ways to the extremities. Notice what I kept saying in there. I kept saying multiply and amplify. And that's what we do in terms of splitting in NMR. So if we do have neighbors on both sides, or however many sides, if we do have neighbors there, then we still apply the n+1 rule. We look at the hydrogens, we add 1. We look at hydrogens on the other side, add 1. And then we have to combo them together. And the way that we do that is we do not add, we multiply them. So 3 times 2 is 6. So for C, what I will find is one major signal. There's our second, there's our third, there's our fourth, there's our fifth, and maybe there's our sixth. There's going to be a split of 6, and sometimes they will use the term sextet. If you wanted to use that term, you could. However, typically undergraduate organic normally stops at 4, and then they just say multiplet after that, and they just leave it. But pentatet and sextet, those are also okay words to use as well. So if you want to use them, use them. If not, multi will be okay here. Okay? All right, so now that we've taken care of C, I'm going to erase some of this pathway to the neighbors. We're going to clean this up a little bit. Get rid of these. And we're going to take a look at now the B. Okay. And this was our D. All right, so now we take a look at B, and B is going to go to the left and say, how many kids do you have? And that carbon's going to say, I've got 3, please. Send them to the, nut house, to the playground, put them out in the middle of the street. I don't care what you do with them, just get them out of my house. And that is going to be +1, so that will be a 4. And then next door to that one, hey, carbon, how many kids do you have? And that carbon's going to say, I have 2. Not as bad as the other neighbor, but I've got 2. They're still bad enough. And we're going to add 1 there, and that will be a total of 3. And then they amplify each other's antics a little bit more. Because of that, they multiply. They don't add. So 4 times 3 is going to be 12. So this B signal, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It might look like a cluster mess like that. And some of these do. Some of these will have a lot of signals, and they will split in many, many ways. But this is what splitting means. So with that said, please be careful. Because this is a true multiplet. But look at now what has happened. It's not just as simple as what I led on to believe, is it? This multiplet has a total of 12. You counted them. There are 12 there. If we have used what we've said in the previous video or videos, there's 12, so therefore there's 12 protons on both sides. How is that even possible? Kind of strange. There's not 12 protons shared between the neighbors. Not for B. We've got 3 on one side and 2 on the other. And then take a look at C. you would look at this and say, oh, that's a sextet. 1, 2, 3, 4, 5, and 6. Well, sextet is 6 minus 1, which is 5. And then you would say, oh, well, there's 5 protons here, right? We've got maybe 3 on one side and 2 on the other. And that's exactly what we have in C, right? And the answer is no, it's not. Look at the C signal. We've got 2 on one side and 1 on the other. We don't have a total of 5. We have a total of 3. And then the same with the multiplet here. Look at this. We don't have 12 minus 1, which is 11. We don't have 11 protons around that signal. I mean, that was for B. What we have there is 3 on one side and 2 on the other. There's not 11. There's 5. So this is where the problem begins to happen with splitting. Sometimes it does match up to the actual total protons on the adjacent carbons, and sometimes it does not. Very often it does not. And that's because molecules are going to be like this one. They're a little more complicated. They have more to them. And because of that, they've got more neighbors with different types of hydrogens that we have to take into account. So very, very often in NMR, what I'm seeing in the signal here in terms of splitting is actually a multiplication of the neighbors. How did we get the 6? I don't really know. It's hard to tell at first glance, right? I don't know what caused us to get 6 in total, or what caused us to get 12 in total. What 2 numbers did we multiply together in order to get that? Right? So this is where the problems of NMR begin, if they've not already began for you. And this is why interpreting splitting is not a 100% perfect type of thing to do. Okay? So it just gives us more information about structure. Maybe if we pair this with something else a little bit later on in the future, we'll be able to help determine this a little bit more. But as of right now, I'm going to have to be careful. I'm going to have to tread very light water, very, very shallow water in order to get to where I'm going. And that's because I don't want to be swamped with this whole misleading splitting issue that we have in NMR. All right, so the next video we'll pick up from here. We'll talk more about splitting, and we'll see where this is going to lead.